So my name is Tim Szigeti. I work on the enterprise architecture team, along with Dave Zaks, whom you've heard from earlier today. And he helped me prepare this story. This is the gates-to-GUI story, but in the context and the view of applications. So he tells the gates-to-GUI story in the terms of like how this benefits routing and fabric and policy management. I'm telling a similar theme story, just like, you know, there's infinite variations of like certain themes like good and evil. There's so many different types of stories. So this particular story is following the why architectural approach is so much better for how we treat and report on our applications. The thesis statement I want to make is that the architectural approach is so much bigger than the sum of the parts, and that's what I want to demonstrate. For DNA, we very much began with a top-down approach, beginning with the end in mind. So that instead of just building something that existed from our tool set, we spent a lot of time with customers. We interviewed in depth over 60 customers. Sometimes, most times, they didn't even know who was asking the questions about the various troubles and obstacles and challenges they had in managing applications on their network. And they helped guide us to present some GUIs that would meet these needs, such as by being able to represent application health at a very high level for applications that are performing poorly and impacting a large number of users to be brought out to their attention. From a particular client's view, if a client calls in and says, I've had a really bad experience on a given application, to be able to see, okay, well, what is the overall health of the application that you ran? And then with a single click to be able to do an end-to-end application path trace complete with jitter packet loss on a per link basis, this type of information to give the user the reasons for that poor application performance. Was it a network issue? Was it an app issue? While this might seem very interesting, it's just the tip of the iceberg. In order to enable this and to make it really happen, there's a whole powerful architecture that we have to build that's very, very deep underneath that surface. And so that's what I want to expand on and reveal and to go into depth on. So the gates to the GUI approach. The overall intent here is to allow for operators to express their application policy in terms of business intent, not QoS policies, not put this into a low latency queue, put that into a CVWF queue, tune WRED, make sure your exponential weighing constant is 6 and not 9, and here's why. We want to say these applications matter, those applications don't matter. Translate that to the best practice, Cisco validated best practices on any given platform. But this is where we've left our customers, and now we have to close that loop, and we're doing this right now. So we're showing that with analytics, we have to correlate all the information from the network and tie it back in the context of did I deliver that expressed intent. If you told me that Skype is important or Skype for Business is important for you, show me how much better Skype for Business is performing. Or if it isn't, let me know that too so I can remediate. Within the DNA architecture, the role of the automation platform is to talk to the infrastructure. The role of the analytics platform is to listen to the infrastructure and then to correlate back to the intent. So a closed loop is what we're building here. Our primary automation platform is APIC-EM, the controller. We're building a platform called Network Data Platform. It's our analytics engine. Internally, we call this Tesseract. That's how you know if anything is real. You always ask, hey, what's the internal code name for this particular product or feature? And if it has one, it's real. If it's not, then it's just an imagination or a wish list. Here's how it all works together. APIC-EM abstracts the complexity of the intent. It takes your intent, and then it will extract the device-specific configuration details, and it will send out the best practices. In turn, then, the network data platform listens to the network from NetFlow, from syslog, from SNMP, from streaming telemetry, any form of input it can gather from the network, and then it has to do all this correlation and contextually tie it back to that particular intent that you've expressed. Either you delivered it or you're not, and you need to remediate. And what's fundamental is we're putting this all below a single pane of glass. You don't know as a user that you're now interacting with the controller, or now you're receiving information from the network data platform. That's completely abstracted. You shouldn't have to go to more than one place. The requirements of the architecture, I'm just going to cover them quickly so that we can show you how we've met these and are building them out. First of all, we have to collect all the relevant metrics specific to how your applications are behaving, not just over the network devices, but we want to collect metrics even from endpoints. For instance, many endpoints can rate adapt. And if they had to rate adapt to, say, a video from 30 frames per second all the way down to 5 frames per second, from a network perspective, it might look very clean. Good latency, low jitter, low loss. But because of that operation, there's a very poor user experience. We want to capture that into the equation as well. We realize that there's so many things that we can keep track of. Not every metric is equally important. Some key performance indicators are more important than others, so we want to flag them as such so that then we can push off these critical messages off the device. Not relying on legacy type of protocols like SNMP to gather information from the network, but rather model-based streaming telemetry. Very efficient, very real-time, and it's very specific to what we're looking for. We want to be able to report real-time or as near real-time as possible. For instance, last year we wanted to do a demonstration to say, hey, we're going to configure policies for APIC EM, and we're going to use our own tool, Cisco Prime infrastructure, to report on those policies. Well, first of all, it's 2 panes of glass, but the real showstopper was that when we configured a policy with EasyQuas, it would take an hour before APIC EM would pick up on that and show some results. If you're an administrator and you've just changed your overall policies, you can't sit around waiting for an hour to see the effect of that. So this is a very critical requirement. There's going to be a ton of information generated from the network. We have to be able to catch that information. Centralized storage, distributed, hierarchical storage, collectors, or cloud-based storage. These are all requirements then so that we can then get all this information, all this data, into a point where we can now start analyzing it, looking for anomalies, looking for interesting correlations, tying it into context, and then taking that data and extracting meaning and ultimately actionable insights from it. We want to be able to then guide users in their troubleshooting, get to that root cause. When you open an attack case, what's the first thing that the engineer asks you for? Show tech, right? He says, okay, you've let me know there's a problem. I want now the full picture. So now instead of just pushing information on the device, I have the requirement to pull, and I might do it contextually. I might start with a show version, and then maybe a show interface, and then a show what a platform counters this or that. And you know, I might go about it that way, or I just might pull the whole thing in. But I have to be able to have more information in order to get to that root cause. We can guide that troubleshooting process and then get to our North Star. And the North Star here is self-remediation. For applications, for example, the #1 attack case for application problems on the network is missing or incorrect classification and marking. If we know this, we can automate some workflows to say, okay, where did that application come into my network? Was there a policy there? Did it match on that policy? Did it mark on that policy according to my strategic requirements? Was that marking preserved end-to-end? Was it mapped to a queue end-to-end? And then, if we keep seeing an issue, we can say, hey, here's a recommended action to take. We see the same same cause again. We recommend the same action. Eventually, we say, do you want to take this action? Yes, 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 always. If we get the operator to that level of confidence where he says, you know what, I've seen that the tool has corrected this. I just want it to auto-correct it from here on forward. That's our path to get to this vision of the network intuitive, the self-remediating network that's constantly learning, it's intent-based policy, it's contextual analytics, and it's a closed loop. So how are we building this? I want to start right from the lowest levels. So let's take a look at hardware. You've seen this with Dave Zaks. Dave Zaks is on our team. I love him. We both work out of the Vancouver office, and he helped guide this presentation as well. So if you're serious about software, build on good hardware. And the focus I want to draw for this discussion is the programmability and the advanced on-chip QoS capabilities. If we can't treat your applications with very granular, very detailed levels of service and report on that treatment, then we can't deliver an overall architecture for you. So starting with, again, the lowest level of electronics, we got transistors. Transistors can send flows from sources to sink depending on whether there's a a signal at the gate or not. We can combine these transistors into logical gates, and we can keep on making these more and more complex. We start with a NAND gate, we invert the operation, and then we have an AND gate, the similar thing with an OR gate. Basically, we take a NOR gate, and then we make an inversion of that, and that's how we get to OR. But all of these gates will always give you the same truth tables every single time, no variation. We want to make that programmable. So how do we introduce programmability to fixed physical hardware? Well, these programmable logic devices allow for fuses to be set in the circuits. And depending on how those fuses are set, the schematic can function as an OR gate, or an AND gate, or an AND gate. And all of these fuses then are set like, say, an NVRAM. You program them, and then the hardware will adapt to what you've programmed it to be. And so now we've taken hardware, we're able then to reuse it in different ways, and it makes it flexible. And that's a fundamental and key concept, because then when we need to support new protocols, as Dave mentioned, or new technologies or features, we can just reprogram the existing hardware without requiring a new ASIC to be spun up. We see that this requires a lot of transistors. You see the increase in the transistors in these diagrams. We went from UADP 1.0 to 2. Or 1.1, went from 1.3 billion transistors to 3, and then excuse me, we went up to nearly 7.5. That's a transistor for every person in the world. That's just really phenomenal power. What that translates to as far as programmability is the ability to program up to 2.1 million lines of code and have it execute in hardware. It's a tremendous amount of power. Pardon me. So my variation of the how small is small is we've taken the largest building, the tallest building in the world, currently the Burj Dubai, and it's nearly twice the height of the Empire State Building. Take a strand of human hair and expand it and say, okay, now a human hair is equivalent to the height of this tallest building in the world. What kind of scales are we talking about? Well, at this scale, a red blood cell would take up about 20 floors. And when we deal with these processes, Intel, for instance, has been in the news lately for doing a 5 nanometer process. That's basically the equivalent of 2.5 of these casino dice that would be lying in front of the tallest building in the world. That's how thin those electrical circuits are being carved out in silicon to achieve this kind of density in the transistors on the ASICs. For UADP specifically, let's take a look at it from the West perspective, which is my favorite area. So if we pop the covers on a switch, we can see these two heat sinks. Underneath there, we have these UADP ASICs. In a multi-gig switch, we have actually 2 dual cores. And if we zoom in on just one of those cores, we see that there's actually more complexity that's presented here. Instead of just having a single forwarding controller, we actually have 2 forwarding controllers, one for ingress, one for egress. We have tables that are shared for common resources like NetFlow or for packet forwarding. We have a recirculation path, so packets can actually go through this ASIC up to 16 times to encapsulate with various protocols, to encrypt, to do all sorts of cool things. We have a scheduler that determines how packets are taken from the buffer and placed onto the stack interface, and how they're received from the stack interface, and then combined with all the traffic that's recirculating or coming from the other cores or other places. So if we take a look at the various functions, we have N-bar applied in these ingress and egress forwarding controllers. We have the ingress queue scheduler. We have a stack scheduler. We have an egress queue scheduler. We have approximate fair drop. We have a dynamic threshold and scaling algorithm. And then ultimately a 2 priority, 6 non-priority, and 3 drop threshold queuing structure on all Ethernet interfaces. The more that you look into this, I love this quote by Peter. It's like, I would always ask him, well, how does this work? And now how does this subsystem work? And how does this subsystem work? And eventually just shooed me off. He's like, stop asking me. If you try to get to the bottom of this, you're just going to drown. There is no bottom when it comes to the complexity of ASICs. Now, here's something that I really love, is that the 3650, this model here, that's also on the 9K, the dual priority queue model, and we added that second priority queue for voice because we would make the argument to our customers saying, you know, video, especially high-def video, is 100 times more drop sensitive than voice. And you've put in voice in your priority queue for 20 years. So you should put video in your priority queue. But here's the reasons for it. And they would say, no, no way. My voice, I'm not messing with it. It's working. Find me an alternative. That's what led us to make a second dual priority queue. It basically, second priority queue interrupts everything else, but it itself could be interrupted if there's traffic in this strict priority queue. But here's why I'm showing this model, is that when we try to explain to customers, why are there 50 different queuing structures in your campus? Well, it's because hardware varies. When we design a specific ASIC for economy, just like you would design a different motor in an engine of a car that's aimed for the economy market, it's going to be a different engine than you would drop into an SUV, which will be a different engine that you're going to drop again into a performance vehicle like Mark's ZR1 Corvette, which he took me in a spin and it blew my hair back. Same thing with ASICs. When it comes to ASICs that we put into our Cat2K switches, the Strider ASIC, that's a different circuit than the K series, the K10 ASICs in our 4500. And they're different from, say, the Earl ASICs and 6500s and so forth. Now, we're always encouraged to adapt our slides to our audience. So this is my American version of this slide. I also have a German version of this slide. I have an Italian version of this slide. I'm Canadian, so when I presented this to a Canadian audience, I had a hard time because we have no native automotive manufacturer in Canada, so this was the best I could use to convey. Hardware varies. But here's what I'm building towards. When you have all these different ASICs, this led us to having over 50 different hardware queuing structures in the Catalyst platforms. This is a nightmare to have to try and figure out a cohesive way to achieve end-to-end.
That really is one of the reasons I never put QoS in my lane.
Exactly.
It really is.
Many people have found the same. The complexity is just overwhelming. Mm-hmm. Whereas with common hardware, UADP 2.0 in 93, 94, 95, now we have a single queuing structure across access, distribution, fixed aggregation. And I'm going to leave it at there because I'm going to get in trouble. So now let's switch to look at a different ASIC. What's happening in our routers? We have the ASR, and under the hood, we have the QFP, the quantum flow processor. With the overall architecture here, it typically will have 2 in a box for redundancy, and that connects all the other line cards, the SPAs, and the Ethernet line cards, etc. Let's zoom in on this. We have the main points, the main interesting areas in this ASIC, especially from an application perspective, is the packet processing array, as well as the buffering, queuing, and scheduling. Did anyone ever see this episode of The Simpsons? Right? But who remembers this router? Right?
Oh, yeah.
Right?
Monster.
Did you like this box?
Monster.
Right?
Yeah.
I love this box.
They're still running.
It's still around, and you know where you can find it? You have 64 of these inside your ASR quantum flow processor. So when you're like, hey, I got a laptop with, a dual core or a quad core, and you're like, hey, that's pretty cool. You got 64 cores inside that QFP chip. I have one in my bag, but to be able to process, and each one of those can process 4 packets simultaneously. So it's 250 packets simultaneously, not per second, but completely simultaneously. Tremendous amount of power. And this also allows us to do a tremendous amount of feature velocity, 2,600 features in this platform alone. Now, the other part that I just love is the buffering, queuing, scheduling subsystem, because there we have 128,000 hardware queues, 5 levels of hierarchy. You want to shape to the service provider subline rate? Great. You want to shape a tunnel? Great. You want to shape to a specific site? Sure. You want to queue within that shaped rate for your applications? Done. You want to also queue by users of the applications, of the site, of the tunnel, of the subline rate? No problem. We'll do it in hardware. That's phenomenal stuff. Then, what's kind of funny, like I said, everything has a code word. So this was a little bit of trivia maybe for you. Maybe you already know it. So the QFP processor was originally 2 ASICs. The packet processor, PPE. It's easy to see where they got Popeye for that. And then Popeye works better if it's got if it has spinach. When spinach was upgraded, became olive, Popeye and olive. We put them together onto a single chip, and then a low-end version of this was called Luke, and the more powerful version of Luke internally was called Yoda. So on that ASIC, I can show you later, you'll see actually a stamp on it that says Yoda. Wireless. Whenever you see a Cisco access point, I don't know if there's one around here, but here's something I want to share under the hood. For every client, we have 8 software queues, one for every user priority value, UP0 through 7. Now, every client, we support 200 clients per SSID. That's 1,600 software queues. And we support 16 SSIDs per radio. So for every Cisco AP, you're going to have 25,600 software queues in order to achieve these levels of service. I think it's pretty cool. It's so under the hood that it's like most of us aren't even aware that this is happening. Beyond this, we not only have to provision for this treatment, you've just heard the discourse on iOS XE, but the part that I really want to focus on with programmatic interfaces, we're able to get information off the boxes. UADP ASIC has 384,000 counters. How are we going to get information off that chip and somewhere where we can actually do some analysis of that information? Well, programmatic interfaces is the key, so that we're not doing SNMP polling, we're not doing screen scraping or something other inefficient means. We want to have a very flexible means of getting the information off the box. Other features on top of software include NBAR, where NBAR, a lot of people think NBAR, oh my God, if I turn that on, I'm going to melt my box. But they're thinking the original NBAR. NBAR 2 is a completely different technology from a completely different source, a PQ acquisition. 90% of packets are flow cached. And of the ones that are processed, we are able to process 40% of them on the first in flow and without even looking at the payload. Some we look at the payload, sometimes multiple payloads. How effective is NBAR? Well, a lot of deep packet inspection engines, especially in this post-Snowden world, will give you results that look like this. It's like, hey, we can't see into your packets because it's all encrypted, so we can't really tell you what's going on. But I'm going to show you screen captures because we have NBAR running here at Cisco Live, and we can recognize 150 applications, even though they're encrypted. We don't rely on deep packet inspection alone. And where does SSL and HTTPS fit in? This is real data taken earlier today, about noon today, that shows all the different applications that users are using here at Cisco Live. And I keep scrolling. This is 1 to 10, 10 to 20. And there we go, number 27. There's SSL. Other applications that are using SSL have already been identified, and only 0.5% of applications, SSL applications, we didn't get a tag on. And as far as HTTPS, it's number 31 in the list, and it's only 0.3%. So very, very powerful classification technology in this engine. Not only that, but for the packets that need multiple packets to be classified, there's traditionally a problem if there's asymmetric routing. If the packet goes on one device in one direction but returns in another, and you needed to see both ends of that flow, how could you make that kind of classification? This is a traditional problem in IWAN scenarios, whereas with SDAVC, software-defined AVC, we're able to stitch that information together and make the classification, and not only make it, but then disseminate the results of that classification to any devices participating in NBAR. Even they don't have to do any deep packet inspection on their own. They just receive the benefits. Now, I actually have one of these Pisa blades. Do you guys remember this one? This was a daughter card on the SOUP 32. I was going to bring it down here to Cisco Live, and my wife's like, because I was packing last minute, she's like, I'm going to help you. I go, yeah, I want to take this also, and it's a nice big heavy box. She goes, if I put that in your garment bag, you don't have any room for clothes. And I'm like, oh, crap, it would have made it a great visual aid. But this was the last time we put NBAR on hardware. Supported 90 protocols. More than half of them were static, like TCP, UDP ports or IP protocols. Maximum throughput 2 gig, and MSRP, as best as I can remember, and I can't find it anywhere else, about 30K. Now we do NBAR on Doppler ASICs. Supports 1,400 protocols, and we add to this every month. We can do 500 connections per second, 5,000 flows on 24 access ports, 480 gig overall throughput, and these switches begin at 3K. So it just shows the value that the hardware is bringing to the, I'm going the wrong way, to the architecture. Now, moving up within DNA at the automation layer, we have tools like EasyQoS that can take business intent as well as have interactions with applications in real time and then communicate those requirements to the network infrastructure, knowing all the Cisco validated best practices of every device. So this is how we can navigate through that ugly complexity of all the different queuing models that have been deployed in our brownfield deployments for QoS and stitch together a holistic, cohesive policy, saving our customers a lot of time, a lot of money. Building on this too, we have a network data platform. And the whole point of this is to take the data, the raw data, and convert that into increasingly valuable information, ultimately actionable insights. Here's an example of what I mean by that. If I have NetFlow record, that can tell me that, hey, there was a flow, I have 5 tuples, source, IP, destination IP, source port, destination IP. Doesn't tell me much other than there was an IP flow. If I add AVC on top of this, now I know, hey, this was the application that was in use. If I combine that with my dynamic DHCP infrastructure, I can find out the MAC address, and that will also tell me the device. Hey, that was a MacBook Pro that initiated that flow. If I include that correlation now with ICE, I know who the user of that flow was and what group he's in, maybe also what other devices he has. I integrate this with topology. I could say, hey, he was associating with this AP, and then I could combine that with location information saying, okay, I know what building that's in. And if I look at information from the network devices, I might say, hey, there's a ton of people in that particular room, and that's why that thing is failing. So this is an example of how we take information from multiple places, correlate them, and thus create the context. And that's context is, again, coming back to this intent and context and learning loop that we want to close. Where does assurance fit in on top of this? It's an application built on top of NDP. And so we want to have views like this to say, look, you'd be able to see your throughput and your overall quality of your applications, and you're going to get this information from a variety of sources. We're going to correlate it all, and we're going to generate then these very accurate health scores that represent what's going on. More than that, we want to integrate with management servers. We want to integrate with data center analytics and also app dynamics itself so that we don't have to rely on users complaining to get ahead of application issues. We want to be able to very quickly isolate whether this is an application issue or if it's a network issue. So we have workflows that we're building into assurance to do this. And then it's funny, I was having conversations with Cisco IT, and I'm like, how do you guys troubleshoot an application issue on our network? And I was embarrassed to hear that the answer is, we use traceroute and pings. And then we look at syslogs and interface stats, and it's like, all right, come on, guys. That's 30-year-old technology. So this is what we're building here is to say, look, with DNA assurance, you have a poorly performing app. You should be able to just do a path trace on that with a single click and get link by link, loss latency jitter, and then see that, hey, there was a difference in the health of the application from one point in the network, and then within context get additional information of what's going on in that device and that queue that the application is assigned to, and then get to that root cause. Automating some of the workflows, I've already talked about, hey, the most common issue is missing classification and marking. How can we automate all of this within the app so that you can speed up that troubleshooting, get to that root cause analysis? We're also adding machine learning. So machine learning where we can take information with so many sources and the algorithm doesn't really know what it's looking for. It's just looking for correlations of normal versus abnormal from so many sources of input and then reporting on them. And then you can help guide that machine learning, saying, yes, this was helpful, this was not helpful, and then it keeps on zeroing in on what you're looking for to give you insights that are just not humanly possible. Hey, from this type of device, accessing that application on this AP at 3 p.m. in the afternoon in the 20th floor of Mandalay Bay, this is the issue that is occurring. To have so many sources of input that have to come together and then have that issue is just beyond a human's capabilities, so you have to have that machine learning. You can do it in various points in time, various places within the network, etc. Then finally, to integrate with app dynamics. If we know what's going on with the application, we can then rule out if it's a network issue or an application issue even faster. We can get that right. We can get the tickets sorted to the right place in the network. And so you don't even have to be an app developer to recognize that, hey, there are metrics that'll tell us, is this normal for this application's performance, or is it poor, or something like that? And then we can go from there. So in conclusion, this is what I want to leave you with, that DNA is an architecture of architectures. From the lowest level, the ASICs, to how they're architected in the switches and the routers, to our software, to tools within our software like AVC or software-defined AVC, to our analytics engine, to our assurance application. It's just a very complex architecture. So if you want to have views like this, we have to have all of these pieces in place to deliver that. And this is what we're building, and I'm very excited to be part of that. So the thesis statement I want to leave you with is that this architecture is greater than the sum of the parts, and Cisco is the only one that can deliver an architecture like this. Thanks so much for bearing with me.
Thanks, Tim.
Thank you.